Today we're going to be talking about how to find local maxima and minima of the function. And in this particular problem, we've been asked to find the local extrema of the function f of xy is equal to x cubed minus 12xy plus 8y cubed. Now the way that we're going to find local maxima and minima is using the second derivative test. And in order to use the second derivative test, we're going to need all three second order partial derivatives of our function f of xy. In order to get to the second order partial derivatives, of course, we need to find our first order partial derivatives. So that's going to be our first step. So finding the first order partial derivatives, we're going to say the partial derivative of f with respect to x is going to be equal to, and here's where we take the partial derivative with respect to x. X cubed gives us 3x squared. Negative 12xy, when we take the partial derivative with respect to x, negative 12y acts as a coefficient on this x variable. We're just left with negative 12y because the derivative of x is 1. So we have 1 times this negative 12y. And then 8y cubed drops away because there's no x variable involved in that term. If I take the partial derivative of f with respect to y, this x cubed term drops away because there's no y variable involved. For my middle term here, I'm left with negative 12x because the derivative of y is 1, and this negative 12x is like a coefficient here. And then the derivative of 8y cubed is going to be plus 24y squared. Those are my first order partial derivatives. Now I want to go ahead and take my second order partial derivatives. So to do that, I'm going to say the second order partial derivative of f with respect to x. Remember, we take the partial derivative of this again with respect to x. That's going to give me 6x. My negative 12y is going to drop away. If I take the second order partial derivative of f with respect to y, my negative 12x will drop away because there's no y variable involved, and here I'll end up with 48y. Now if I take my mixed second order partial derivative, x, y, what I end up with here, if I start with the first order partial derivative with respect to x, and I take the partial derivative of this with respect to y, now my 3x squared drops away because there's no y variable involved. I'm just left with this negative 12 here, so I get negative 12. Now that I have all of my first and second order partial derivatives, my next step is to find critical points of this three-dimensional function. The way that I'm going to find critical points is by setting my first order partial derivatives, we're going back to those, by setting my first order partial derivatives equal to 0. So I'm going to say 3x squared minus 12y is equal to 0, and I'm going to say negative 12x plus 24y squared is equal to 0. Now I want to simplify these as much as I can. If I divide through this equation by 3, I'll get x squared minus 4y equals 0. If I divide through my second equation by 12, I'm going to get negative x plus 2y squared is equal to 0. These equations are simpler than my original first order partial derivatives. Now what I want to do is solve this as a system of simultaneous equations. So I want to take these two equations here and use them as simultaneous equations that I can solve for x and y. So probably the easiest way to go about doing that, and there's lots of ways to approach it, but if I start with this second equation here and I add x to both sides, I've immediately solved for x in terms of y. So adding x to both sides here gives me 2y squared is equal to x. Since I have a value for x in terms of y, I can plug that into my first equation directly. So here's what that looks like. Plugging in for x, I get quantity 2y squared because I plugged in this 2y squared here in for x right here. So 2y squared minus 4y is equal to 0. Now this equation I can solve for y. Here's what that's going to look like. I'll get 4y to the fourth minus 4y is equal to 0. If I pull out a 4y, I'm going to get 4y times y cubed minus 1 is equal to 0. Now if I solve this for y, I look at each factor individually. I would set 4y equal to 0 and get y equals 0. If I say 4y is equal to 0 and solve that, I get y equals 0. Now if I take y cubed minus 1 and set that equal to 0, I'd add 1 to both sides to get y cubed is equal to positive 1, and the only answer then that makes sense for y is y equals 1. So the two values I found for y were y equals 0 and y equals 1. What I need to do now is find corresponding values of x for both of these y values. And the way that I'll do that is by plugging these y values into this equation here for x. So when I do that, I'll plug in y equals 0. I'll get x equals 2 times 0 squared, which is going to give me x equals 0. If I plug y equals 1 into this equation, I get x equals 2 times 1 squared, which is going to give me x equals 2. So now, coming out of this first row here, these two values, I'm going to get the coordinate point 0 and 0. So I have my first coordinate point 0, 0, and then coming here out of my second row with y equals 1 and x equals 2, I have the coordinate point 2, 1. So I have two coordinate points which are my critical points. In order to use the second derivative test to evaluate these critical points to see whether or not either of them is a local max or a local min, I need to plug these points into my second order partial derivatives. So here's what that looks like. When I evaluate this second order partial derivative at the point 0, 0, I'm going to plug 0 in for x here and get 6 times 0, or just 0, so my value is 0. When I evaluate it at the point 2, 1, I plug in 2 for x and get 6 times 2 is equal to 12. When I evaluate this second order partial derivative at the point 0, 0, I do 48 times 0 and get 0. When I evaluate it at 2, 1, I plug 1 in for y and get 48 times 1, which is 48. Doing the same thing for our mixed second order partial derivative, plugging in 0, 0, I'm going to get negative 12. There's no variable to plug in for. Plugging in 2, 1, again, I'm going to get negative 12 because there's no variable to plug in for. These are the values I'm going to need to plug into my second derivative test to figure out whether or not these critical points are local max, local min, or neither. So here's what my second derivative test looks like. If you ever look at the definition of the second derivative test or the formula you're going to use, it looks a little bit complicated, but in actuality, it's not that complicated. The notation just makes it look more complicated than it actually is. We call the value that we're going to find here with the second derivative test d. So we're going to say d of 0, 0. In other words, using the second derivative test to evaluate the critical point 0, 0 is going to give us, and here's where we use the values we just found. We do the second order partial derivative with respect to x at our critical point, so that's this value here. We plug that in, so we say 0. Then we multiply that by the second order partial derivative of f with respect to y evaluated at our critical point, and that we found here, so that's going to give us 0. Then we subtract the mixed second order partial derivative evaluated at the critical point, which was negative 12. We take that negative 12 value and we square it. So that's our formula. Second order partial derivative with respect to x times second order partial derivative with respect to y minus the square of the mixed second order partial derivative. And when we simplify this, obviously we get 0 here. Negative 12 squared gives us a positive 144, but we have this negative sign out in front here, so we get minus 144. That's the value of d at the critical point 0, 0. D of the critical point 2, 1 is going to give us, here we take 12, we multiply it by 48, and then we subtract quantity, negative 12 squared. So we just plugged in 12, 48, and negative 12 in the same way that we plugged in 0, 0, and negative 12. And when we simplify here, we're going to get a value of 432. Now these values, here's where our second derivative testing really comes in. We're looking at these two values to see whether or not they are positive, negative, or equal to 0. So obviously negative 144 here is less than 0, 432 is greater than 0. When it comes to the second derivative test, if the value you get for d is equal to 0, then the second derivative test is inconclusive. You can't use the second derivative test to draw a conclusion about the critical point, and you need to test it in some other way. Obviously, neither of our values for d are equal to 0, so that doesn't matter. But if you get a value that's equal to 0, then the second derivative test is inconclusive for that critical point. If the value you get for d is less than 0, as in the case of our critical point here, 0, 0, where we got a negative 144, that's less than 0, then this critical point represents a saddle point. It's neither a local maximum nor a local minimum. So we'll say that our critical point 0, 0 here is a saddle point like this. So that's what we know if the value of d is less than 0. If the value of d is greater than 0, as it is for our critical point 2, 1, we need to turn to the second order partial derivative with respect to x. So because we're dealing here with the critical point 2, 1, we want to look at the second order partial derivative with respect to x at the point 2, 1. That's this value right here, 12. So both of these values are going to come into play. So because the value of d is greater than 0, we have to turn toward this value here. Now, if this value is greater than 0, then the critical point represents a local minimum. If this value is less than 0, then the critical point represents a local maximum. Because this value is greater than 0, we know that 2, 1 is a local minimum, and we can draw that conclusion. If this had been negative 12 or some negative number, then we would say that 2, 1 was a local maximum instead. So now that we've drawn conclusions about both of our critical points, and we can say that 0, 0 is a saddle point and 2, 1 is a local minimum, we've got our final answer. That's how you use the second derivative test to find local maxima and local minima of a multivariable function.